3 days ago, a meteorite that had been sitting in a museum collection for decades gave up a secret that nobody expected it to be. Carrying, scientists analyzing its internal structure found something that should not exist inside a rock that fell from space. Evidence of a world, a complete world. A planet the size of the moon that formed in the early solar system, lived briefly in cosmic time, and was then destroyed in a collision so violent that the only evidence it ever existed is now locked inside the chemical structure of a meteorite sitting in a laboratory. This discovery was not made by pointing a telescope at the sky. It was made by cutting open a rock and looking at what was inside it. And what was inside it has just rewritten what we thought we knew about the earliest days of our solar system. To understand why this finding matters so much, you need to understand something about how our solar system formed. 4.5 billion years ago, our solar system did not look anything like it does today. There was no Earth, no Mars, no Jupiter in its current position. There was a young sun surrounded by an enormous disk of gas and dust, and within that disk, a violent and chaotic process of collision and growth was underway. Small particles collided and stuck together, forming larger particles. Larger particles collided and formed rocks. Rocks collided and formed boulders. Boulders collided and formed objects called planetesimals, which are essentially the building blocks of planets. And planetesimals collided with each other, forming the planets we know today. But here's what most people do not realize about this process. It was not clean. It was not orderly. For every planet that successfully grew large enough to survive, there were dozens or hundreds of smaller worlds that formed, developed, and were then destroyed, shattered by collisions with larger objects, broken apart by gravitational interactions with the giant planets that were forming in the outer solar system, consumed by the growing Earth or Mars or Venus. The early solar system was full of worlds that no longer exist. Worlds that formed, developed internal structures, perhaps even geological activity, and then were erased from existence before any life had time to emerge, before any telescope existed to observe them, before any human was there to know they had ever been real. We have always known these lost worlds existed in theory. The mathematics of planet formation demands them. The models require them. But actually finding direct physical evidence of one, actual material from an actual destroyed world, has been one of the holy grails of planetary science for decades. And 3 days ago, a meteorite delivered exactly that. The meteorite in question is classified as an iron meteorite, a category of space rock that forms from the cores of planetesimals that were large enough to undergo a process called differentiation. Differentiation is what happens when a rocky body grows large enough that its interior heats up, either from the decay of radioactive elements or from the energy of collisions, until the material inside it melts and separates by density. Heavy metals like iron and nickel sink toward the center, forming a metallic core. Lighter silicate rocks float toward the surface, forming a mantle and crust. This is exactly what happened to Earth. Our planet has an iron core, a rocky mantle, and a thin crust. The process of differentiation that created this structure happened very early in Earth's history when the planet was still. Partially molten iron meteorites are fragments of the cores of ancient planetesimals that underwent the same process and were then destroyed by collision. When two differentiated planetesimals slam into each other, the collision can shatter both of them, scattering fragments of their cores, mantles, and crusts across the solar system. Some of those fragments eventually find their way to Earth as meteorites. Scientists have long known that iron meteorites represent material from destroyed worlds. What they did not know until now was that some of those destroyed worlds were significantly larger than anyone had calculated. The research team that analyzed this specific meteorite used a technique called high-precision isotopic analysis, which measures the ratios of different isotopes of specific elements locked in the rock's crystal structure with extraordinary precision. The isotopic signature of a piece of metal tells you something about the pressure and temperature conditions under which it formed, which in turn tells you something about how large the body it came from was. When large planetary bodies form and differentiate, the extreme pressure at the center of the body affects how certain elements and isotopes distribute themselves within the metal of the core. The larger the body, the higher the core pressure, the more distinct the isotopic signature of the core material. The isotopic signature the team found in this meteorite corresponds to a core pressure that requires a body significantly larger than any previously known destroyed planetesimal. The calculations the team ran suggest the parent body of this meteorite was approximately the size of the Moon, perhaps slightly larger. Large enough to have a fully developed metallic core, a rocky mantle, a crust, and potentially a geological history of its own before it was destroyed. A moon-sized world. Gone. Destroyed before Earth even fully formed. And the only evidence it ever existed is this meteorite. Now here is where the story reaches into something that the research team acknowledges openly in their paper and that the broader planetary science community is still processing. If a moon-sized world existed in the early inner solar system and was destroyed, where did the material go? Collisions of that scale do not make things disappear. They scatter material. The shattered remains of a moon-sized world would have contributed to the formation of the existing planets. Some of it became Earth. Some of it became Mars. Some of it became Venus. Which means that right now, locked in the rocks beneath your feet, there is material from a world that no longer exists. A world that had its own geological history, its own core, its own surface, and which was destroyed so completely that until 3 days ago we had no idea it had ever been real. The implications for understanding Earth's own formation are significant. One of the longest-running puzzles in planetary science is the exact sequence of collisions and mergers that built Earth to its current size. We know the broad outlines. We know that Earth formed through the accumulation of planetesimals. We know that a large impact late in Earth's formation created the Moon. But the specific catalog of what worlds contributed material to Earth, how many of them there were, how large they were, has always been incomplete. This discovery adds a new entry to that catalog. A moon-sized world whose destroyed remains were available as raw material in the early inner solar system at exactly the time when Earth was growing toward its final size. The research team's paper, published this week in a major planetary science journal, stops carefully short of claiming they know exactly which planets received material from this lost world. The isotopic evidence tells them the parent body existed and approximately how large it was. It does not tell them where precisely its material ended up, but the implication is unavoidable. Whatever this lost world was, wherever it formed, whatever brief geological history it had before it was destroyed, part of it is now part of us, part of the Earth, part of the Moon, possibly part of every rocky planet in the inner solar system. The question the planetary science community is now asking is how many more of these lost worlds are hiding in meteorite collections around the world. The isotopic analysis technique the research team used is relatively new and has only been applied systematically to a small fraction of the thousands of iron meteorites in museum and research collections globally. Each of those meteorites is a fragment of a destroyed world. Each of them potentially carries an isotopic signature that could tell us something about how large that world was. If this meteorite came from a moon-sized world, what might the others reveal? That question is now being asked in laboratories across the planet. Teams with access to the new isotopic analysis techniques are beginning systematic surveys of iron meteorite collections, looking for more signatures of large lost worlds. What they find will fill in the picture of the early solar system in ways that computer simulations alone never could. Because simulations are built on assumptions, meteorites are actual physical evidence, actual material from actual worlds that actually existed. 3 days ago, a rock told us something about our past that we had not been able to learn in any other way. And the message it carried is simple and extraordinary. Our solar system was once home to more worlds than it is today. Worlds that formed, lived briefly in geological time, and were destroyed in the violence of the early solar system's formation. Worlds that contributed their material to the planets that survived. Worlds that are, in a very real physical sense, part of everything we see when we look at the solar system around us. We are made partly from worlds that no longer exist, and we are only just beginning to find out how many of them there. We're subscribed to Sky Pulse. Turn on every notification. The solar system has more history than anyone imagined. This is Sky Pulse. Stay alert. We will see you in the next one.